Okay, here's where we left off. Suppose you deposit $1,000 every 6 months into an account that earns 4% compounded semi-annually. Now this is as opposed to putting a lump sum into an account and just waiting for the 3 years. So at the end of a 6-month period, we have $1,000 balance. We're going to accrue interest on that. And so the beginning of the second 6-month period will have $1,020 in the account. At the end of that period, we're going to add $1,000. So we end up with a balance of $2,020 at the end of the second 6-month period. Okay, that's going to earn interest. The amount of interest will be the 1.02 times this balance $2,020, which will give us $20.60 We add that $1,000 to that, and we end up after the third 6-month period with $3,060.40. And we just continue this process. So at the beginning of the fourth 6-month period, we will have had $30.60.40 plus the interest that it earned, and we're adding to that the next deposit of $1,000. So we just follow this and it keeps filling in the account. At the end of the sixth 6-month period, in other words after 3 years, we end up with $36.08.12. Okay, there's a formula that we'll use for this instead of having to do this all out every single time. So to begin with, an annuity is a sequence of equal periodic payments. And the future value of an annuity is the sum of all the payments plus all the interest earned. We use the future value formula if the money is being accumulated periodically for some time in the future. So here's the formula. Future value equals payment times 1 plus I, that's the same I, to the n minus 1 over I. So PMT stands for the fixed periodic payment. I stands for the interest rate per period, like we had before. N stands for the total number of periods, again like we had before. And FV stands for the future value. So we'll do some problems here. What is the value of an annuity at the end of 10 years if $600 is deposited every 6 months at 6.5% compounded semi-annually? And then we'll answer the question, how much interest is actually earned here? So we'll start with the interest rate per period is 0.065 divided by 2, or 0.0325. That's I. And there are 20 total periods, twice a year for 10 years. So n equals 20. So we know the payment is $600 every 6 months. I equals 0.0325. That's the interest rate per period. And there are 20 periods. Here's the formula. So we just plug in those numbers where they belong. So the future value equals 600 times 1 plus 0.0325 to the 20th minus 1, all divided by 0.0325. Now remember to do this in steps. We add the inside the parentheses first, then raise it to the power of 20, then subtract 1, and then divide by 0.0325. So in this step I have the parentheses raised to the 20th power, that's the 1.89, etc. I subtract 1 and then divide that by 0.0325. The result of that whole mess is 27.564. Multiply that by 600. That means at the end of this time period, there will be $16,538.55. That's the total amount after 10 years. Okay, now to calculate the amount of interest earned. No, well, how much did we pay into this account in the first place? We got a lot of money, we got a lot of interest, but we also put in a lot of money. There were 20 deposits of $600, so a total of $12,000 was deposited. That's 20 times 600. The difference between the ending balance, the $16,000, and the total deposits is the amount of interest earned. So in this case, 16,538.55 minus the 12,000, we got $4,538.55 just in interest. Okay, here's another problem. You deposit $200 at the end of each month at 6% compounded monthly for 3 years. How much will be in the account after 3 years? The interest rate per period, I, is 0.06 divided by the number of periods per year, 12, or 0.005. And there are 12 periods per year for 3 years, so there are a total of 36 periods, and equals 36. And the monthly payment is $200. So once again, we'll use this formula, and we know these numbers. So payment is 200, I equals 0.005, n equals 36. Plug all of that into the formula, and then simplify and solve as much as you can. So I'll combine the parentheses first, raise that to the 36th power, and I get 1.19668. Subtract 1 from that, and then divide by 0.005. That number, the fraction there, equals 39.336. Multiply by 200, and that's the amount after 3 years. Okay, we'll try something a little different here. The parents of a newborn decide that on each of the child's birthdays up to the 18th, they will deposit some amount into an account that pays 6% compounded annually. What amount should they deposit each year in order to have $80,000 after the last deposit? Notice this again is a future value. We're putting money into an account periodically in order to have an amount later. So in this case, we have $80,000 is the amount we want in the future. So what we really want to find out is how much the periodic payment needs to be in order to meet that goal. So we've got the same formula. We know that we want to end up with $80,000. That's the future value. I, in this case, is just 0.06 since it's compounded annually. And there are 18 total periods. So we take all of that and plug it into the formula. And in this case, we want to solve for PMT, for the payment. Do the same thing. Combine the 1 plus the 0.06, raise that to the 18th power, subtract 1, and the top becomes 1.85434. Divide by 0.06. We get 80,000 equals the payment times 30.9, etc. Divide by 30.9057. So the amount of each annual payment is $25.8852. That's how much we have to deposit into the account each year in order to end up with $80,000 in 18 years. By the way, this is an example of what's called a sinking fund. It's just a term. It's an account that's established for accumulating funds to meet some future obligation. It still uses the same formula, the future value formula. Okay, here's a little more complicated example. Jane deposits $2,000 annually into a Roth IRA that earns 6.85% compounded annually. She stops the deposits after 10 years, but the account continues to earn interest until Jane retires 25 years later after the last deposit was made. How much is in the account? So we have two pieces here. There are 10 years of periodic payments, followed by 25 years of just having the money accrue interest. So we'll do it in pieces. First, find the amount in the account after 10 years. This involves the future value of an annuity because we're putting periodic payments in over a period of time, and it's accumulating money. So we use the future value formula here. She's putting 2,000 in. The interest, the I is 0.0685 divided by 1. It's annual. And this is for 10 total periods, 10 years. So you know the drill here. We run this through and we get, after 10 years, Jane has $27,437.89. So now that money is going to sit in an account just collecting interest. That's a regular compounding problem. So we use the compound interest formula. It's no longer we're no longer putting deposits in, it's just sitting there. So the amount, we just plug in the values. The principal is how much we started with, $27,437.89, times 1 plus 0.0685, and to the 25th power, because we're doing 25 years. So we do some of the calculation. So after a total of 35 years, this is how much is in the account, $143,785.10. That's it.